Okay, HSC Chem, exam calculations. So I've pulled out a few examples and I'm going to go through some worked examples of these calculations, hopefully help you better understand some of these calculations that you're going to come across in your exams. Which concentration of hydrochloric acid would have the same pH as a solution of 0.5 mole acetic acid? The Ka of acetic acid is 1.8 times 10 to the negative 5, so they've given us a little bit of information there. They've also given us the concentration of the acetic acid, but how can we use what they've given us to work out the concentration of HCl? Well, let's go ahead and have a look at this equation here. When this weak acid, acetic acid, dissociates in water, for every one molecule of that acid, we get one molecule of H3O, hydronium, and one molecule of acetate ion, or the conjugate base. By definition, the pH is the negative log of the concentration of H3O. Now, pH is in the question here, and you'll often find that this is a really important part of these types of questions when they talk about Ka and pKa and Kb and all of this kind of stuff. They're looking at this here, the concentration of H3O. If we can work that out, then we can work out many other steps as well. So to start with, we're going to write an equilibrium expression for this dissociation, which is Ka is equal to the concentration of our products. There's our H3O. Remember, the negative log of that concentration is pH. It's pretty handy. So CH3COO, the concentration here of the conjugate base, yeah, it's not really that important here. But we put it in anyway, obviously, and that's going to be over the concentration of our reactants, which is the acid itself, the concentration of the acid itself. Don't worry about H2O. It's a liquid. It doesn't go in the equilibrium expression. All right, lovely. Now we can start filling this out, and keep in mind that for every time one of these molecules here dissociates, we get one H3O and we get one CH3COO, or acetate ion. So these two concentrations are going to be the same. We're going to have X and X. So we can start filling this out even further now. They've given us Ka and say that 1.8 times 10 to the negative 5 is going to be equal to X times X, or X squared, over the concentration of the acid. Have a look at the question. They've given us that. 0.5 mole acetic acid. 0.5. Lovely. Okay, let's solve for X. Rearrange. And remember, solving for X is going to be giving us our concentration of H3O. So this is an important step here. X is going to be equal to the square root of 0.5 times 1.8 times 10 to the negative 5. So that means X is 0.003 molar. X is the concentration of H3O, which is 0.03 molar. Now, leave it there and have a look at what the question's saying. What concentration of hydrochloric acid would have the same pH as a solution of 0.5 mole acetic acid? For them to have the same pH, they must have the same concentration of H3O, right? That makes sense. Now let's have a look at HCl. HCl is a strong acid. It will completely dissociate in water to give us H3O and Cl ions, right? So whatever the concentration of hydrochloric acid, that will equal the concentration of H3O because it dissociates completely. It's pretty straightforward. Therefore, to have the same pH as our acetic acid here that we've just worked out, it must have a concentration of 0.03 molar. So the answer here is D. So we need to find the pH of a 0.015 mole solution of a weak monoprotic acid. They've given us pKa, which is okay. We're just going to turn that into Ka, and it's just like working with pH going back to the concentration of hydronium. It's the same process. So pKa is the negative log of the Ka. So to work out Ka, which will be our starting point, we need to do 10 to the negative 5.5, and that's going to be equal to 3.16 times 10 to the negative 6. So we've got our Ka value, and we know that for a weak monoprotic acid, we've got H plus as a product. We've also got the conjugate base as a product, and that's a 1-to-1 ratio, and that's going to be over the concentration of whatever acid happens to be. And remember, the concentration of H and A at the top here will be the same, so we can assign them as X. Okay, Now that we have Ka, let's write out our equilibrium expression, and we're going to say 3.16 times 10 to the negative 6 is going to be equal to x squared, and yes, they've given us the concentration of this generic weak monoprotic acid, 0.015. Remember, we're solving for x, and x is going to be concentration of hydronium ions, which we can work out pH from. Beautiful. X, or the concentration of H3O, which is what we're interested in, is going to be equal to the square root of 0.015 times 3.16 times 10 to the negative 6, which is going to equal 2.178 times 10 to the negative 4. Okay, so that's X, and remember, X is our concentration of H3O. We need to work out the pH of this solution. Easy done. Let's say that the pH is equal to the negative log of that, which is 3.66. Right, well, that should be the pH of this particular solution. Have a look at the answers up here. You can round that to 3.7 being the correct answer. There's a couple of distractors here. They've got 5.5, in case someone was thinking, I don't know, for some reason that was the same as that. 0.000218 here, this little distractor, well, that looks very similar to this concentration here. But it's not the pH, it's the concentration of hydronium ions. It's one stop short of the correct answer. And what's the other one? They've got 10 to the negative 5.5. I don't know, I guess people might have thought, yeah, well, that's the first step, and somehow that's the answer? I don't know. But we know by taking the pH here, taking the negative log of that concentration, correct answer is 3.7. So we need to find the pH of a saturated solution of manganese hydroxide, and we're going to use KSP to find that. You can see in our formula here, manganese hydroxide would associate to form 2 moles of hydroxide for every 1 mole. Here we go, 2 moles of hydroxide for every 1 mole of manganese hydroxide. We're going to find pH. It looks like in our KSP expression we're going to find the concentration of OH, so that's going to be important. And then from our concentration of OH, it's fairly straightforward to work out pH. So that's the plan. We're going to plug it in to our KSP expression, solve for our unknown, which are the concentrations here of hydroxide and manganese, and then work out our pH. So they've given us the KSP value in the question, which is 2.0 times 10 to the negative 13 is equal to, now these concentrations are unknown, so we're going to say this solubility here is S, and remember we're forming for every 1 manganese 2 hydroxide, so this is going to be 2S. So we can say that the KSP is going to be equal to S multiplied by 2S, and don't forget to square it as well, 2S squared. That would be 4S cubed if we expanded that out. So let's solve for S, and that's going to give us our concentration of manganese, and 2S is going to be our concentration of hydroxide. So we're getting somewhere. S is equal to the cubed root of 2.0 times 10 to the negative 13 over 4, which is 3.68 times 10 to the negative 5. So that is the concentration of manganese ions. 2 times that, 2S, is our concentration of hydroxide. So concentration of OH is going to be equal to 2 times S, which is going to be equal to 2 times 3.68 times 10 to the negative 5, which equals 7.37 times 10 to the negative 5. So this is our concentration here of OH. We need to find pH, so only a couple of steps left to go. Hopefully you can see where to go from here. I'll come back up here because I'm running out of room. 7.37 times 10 to the negative 5 POH is going to be the negative log of 7.37 times 10 to the negative 5, which is 4.13. So the POH is 4.13. pH, this is what we need to find for this question here. pH is equal to 14 minus 4.13. So we can round for sig figs here. and say pH is 9.9. So when you're working out these questions that involve pH, pOH, KSP, maybe KB, look for concentrations of hydroxide ions or hydronium ions, so we can work out pHs and pOHs, etc., to solve for these types of problems. When you're working through titration problems like this, which are multi-step, you've got multi-parts, sometimes it's kind of handy to draw a little sketch of the setup, including all of the volumes of solutions that are made up or diluted, for instance, and you can keep track of what's being transferred to where, what's in the burette, what's in the conical flask, and sometimes to visualize where these volumes and numbers are going, it can be easier than just looking at a paragraph of volumes and concentrations and titers. So sketching things out can help. I've sketched out a little dodgy titration in the bottom left here. I've got 3 little beakers, not volumetric flask, but it's okay. The point is I have containers where I can see my volumes and what I'm transferring where. Also, you should start with a balanced chemical equation because titrations are all about the moles, man. So you've got to keep track of moles. And a balanced chemical equation with coefficients will allow you to do that. So put down your balanced chemical equation for the titration. Any other equations, if there's a couple of titrations or standardizations that you need to do, put all of those chemical equations down, then maybe sketch it out like I have, and then we can begin. Let's start from the top of this problem here and have a look at what we need to do. 3.2 grams of sodium carbonate, weighed, dissolved, transferred to 500 ml and filled to the mark with distilled water. So this here, we're just making up a primary standard. I'm assuming that's one thing they're going to ask us to determine. What's the concentration of that primary standard? Let's work that out. So we're going to need a number of moles. Titrations, like I said, all about the moles. Let's find out how many moles we have. Na2CO3 is going to be equal to our mass, which is 3.2 grams, over the molar mass of sodium carbonate, which is 106. That gives us 3.02 times 10, -2 moles. All right, so now that we've got our moles, we have a volume. Brilliant. Let's work out the concentration of this guy, of our primary standard, Na2CO3 is equal to N over V, which is equal to, I'll write it out again, 3.02 times 10 to the -2 over volume, 500 mil, so that'll be 0.5. That is going to be equal to 6.04 times 10, -2 molar. That's the concentration here of our primary standard. So that step has been done. Beautiful. We've worked that out. Got our concentration. Let's have a look at what we've got to do next. Actually, you know what? Let's annotate our diagram so we can see what we've done. Let's just say that in here we have 500 mil and it's 6.04 times 10 -2 m and it's Na2CO3. Okay, so that's what's in this little flask down here. 25 ml of this solution was then transferred into a conical flask. Okay, so we have taken 25 ml of that, and that's in our conical flask. We have 25 ml of that solution. Okay, done. 10 ml of a solution of HCl. This little beaker down here on the right here is, let's say that this is volume 1, and it is 10 ml. We don't know the concentration of this first solution yet, so we're going to leave that blank. So 10 ml was transferred to 250 ml, filled to the mark with distilled water. Okay, let's just say in our next beaker here, volume 2 is now 250 ml. Concentration 2, and we don't know that yet either. Those two, C1 and C2, the diluted and the undiluted solution concentrations, I'm assuming that's what they want us to figure out here. So yeah, we've done our transfer, we've done our dilution, we don't know the concentration of those two because we haven't done the titration yet. Excuse me, that's our next step. Burette filled with HCl, right? So in here, we have HCl. Following tighter volumes obtained, we can get rid of the 12.7, it's an outlier, which gives us an average of 11.45 mil. So HCl, 11.45 mil. All right, using what we have here, let's go ahead and try and calculate some moles and some concentrations as we go. And we're going to start with, let's work out the number of moles, we can do that, of sodium carbonate. We have a concentration of sodium carbonate and we have 25 mils of it. So let's do that first. Start with what we know. Number of moles in that conical flask of Na2CO3 is going to be equal to C times V, which is going to be equal to, concentration was 6.04 times 10 to the negative 2 times 0.025 litres, and gives us 1.51 times 10 to the negative 3 excuse me, moles. All right. Now this is where your balanced chemical equation is going to come in handy, because we can then work out, that was a titration, so we neutralise that with hydrochloric acid. Let's use our molar ratio to work out the number of moles of HCl. All about the moles. We're going to calculate moles to get our concentrations. Excuse me. According to the balanced chemical equation, we do the following: 2 over 1 multiplied by, so 2 times 1.51 times 10 to the negative 3 gives us 3.02 times 10 to the negative 3 mole. Lovely. So now we've got the number of moles of HCl. We can go ahead now and do concentration. So our concentration, and this will be, because we put our dilute HCl into the burette, this is going to give us concentration 2 here. So our concentration is going to be of HCl is C equals N over V, moles per litre. We had 3.02 times 10 to the negative 3 over, and what was our mean titer? 11.45. So that gives us 0.01145 N over V, moles over volume. 2.64 times 10 to the negative 1, or you could say that this is 0.26 molar. That is the concentration of our dilute. Remember, we put this 250 ml dilute solution into our burette. So therefore C2, if we go back over to our diagram here, concentration 2 is 0.26 m. Okay. The next step would be to work out, well, what was the concentration of that initial 10 mil, that little beaker we have over here, this guy? What was the concentration of that? Well, we've got V2, C2, we've got V1. This is pretty straightforward. We're going to do C1, V1 equals C2, V2. We're going to follow the moles, and we can say here that we will have 0.26 C2 multiplied by 0.25 V2 divided by 0.01, which was V1, and concentration 1 would therefore be 6.5 mole. So there we go, this is 6.5 molar HCl. So that's how we worked out this particular question here. Start at the top and break it into parts, I guess, and start from the beginning, and keep track of things possibly if you like. It makes it sometimes easier to visualize this and draw beakers and draw your experimental setup and follow the bouncing ball. Where do these solutions go? Where are they being diluted? That can sometimes help. And please always put in your balanced chemical equation as well, so you can keep track of molar ratios, etc. Okay. All right, this one's fairly straightforward. We define the term weak acid, classify acid X as either a strong or a weak. Okay, let's just say a weak acid. Weak acid does not fully ionize, and strong, weak, and give reason. We're going to say that this is a weak acid. X is weak due to small Ka value. That Ka value tells us that the equilibrium lies far to the left, that small equilibrium constant. So therefore it hasn't ionized very much at all, so we'd classify that as a weak acid. Moving on to determine the pH of that's concentration of acid X. That's fairly straightforward. We can say that Ka is going to be equal to whatever this particular acid is. The general formula here is A minus. So the concentration of hydronium ions and the conjugate base, which are the products of the dissociation over the concentration of the acid itself, is equal to the Ka. They've given us Ka, which is 1.64 times 10 to the negative 5. Excuse me. And we know that when this monoprotic acid dissociates, we get one of those and one of those, one of the H plus and one of the conjugate base. So we can assign both of those concentrations as X. They're going to be the same, which means Ka is equal to X squared over the concentration of the acid. And yep, they've given us the concentration of the acid here, 2.43 times 10 to the negative 3. 2.43 times 10 to the negative 3, rearranged to solve for X. And remember, when we solve for X, we are going to be solving for the concentration of H plus, of which we find the negative log, and we have pH. So let's go ahead and say X is equal to square root of 2.43 times 10 to the negative 3 times 1.64 times 10 to the negative 5. Give me 2 seconds to work that one out. Turn on would help. Square root. .64 1.996, so 2 times 10 to the negative 4. X is equal to 2 times 10 to the negative 4. So that is so therefore we can say that the concentration of H3O plus is equal to 2 times 10 to the negative 4. And I'm out of room here, guys. Apologies. I'm going to put it up here. The next step is to say that the pH of this solution is going to be the negative log of 2.0 times 10 to the negative 4, which equals 3.7. 3.70. 3.70. We're going to round that up. 3.70 is our pH. Okay, for this multiple choice, there's a fair bit of work here for 1 mark. What are we looking at? Sodium ethanoate dissolving in water, the following reaction takes place. We can see that we're forming OH, so we're going to have a basic solution. Based on that, pardon the pun, but based on that, we can get rid of A and B because they're both acidic pHs. So already you're down to a 50-50 choice for 1 mark. There's a fair bit of work that's going to go into making sure we get that 1 mark. And if you want to go through the whole process of working out which of those pHs is correct, there's a few steps we're going to have to go through. First of all, if we're making a basic solution, we can't use Ka, we've got to use Kb. We need to use that equilibrium expression rather than the Ka. Starting with pKa, let's just start at that point and say, well, let's turn our pKa into Ka, which we can work with. So our Ka is going to be equal to 10 to the negative 4.76, which is going to give us 1.74 times 10 to the negative 5. Great, so we've got Ka, but remember we need Kb to put into this base dissociation constant. Kb, so what's the relationship between Ka and Kb? How do we get there? Ka times Kb equals Kw, the auto-ionization of water, constant. And Kw is equal to times 10 to the negative 14, which is the basis of our pH scale. So we've got Ka, we've got Kw, we know what that constant is. We need to work out Kb to put it into our expression in a second. So let's say that Kb is equal to, we'll rearrange this and say 1.0 times 10 to the negative 14 over Ka, 1.74 times 10 to the negative 5. That's going to give us 5.75 times 10 to the negative 10. That's our Kb value. So now we have that, we can go ahead and based on our equation up here, we can get a Kb expression happening. So I'm going to put that up the top here and say our Kb is going to be equal to concentration of our products, CH3, so this is the conjugate acid that's formed, the OH, hydroxide, and keep an eye on that, that's important. Remember, with these kind of questions, you're always trying to solve for the unknown concentration of hydronium or hydroxide, and then we can work out pHs and pOHs from that. And we have CH3COO as our reactant. All right, so we have a 1-to-1 ratio for the acid and the hydroxide concentrations above. So again, we can assign both of those as X and start filling in our expression here. So have they given us, oh no, we worked out Kb, that's right. So 5.75 times 10 to the negative 10 is going to be equal to X squared over concentration, 0.42, 0.42, okay, and that will give us, X will be equal to the square root of 0.42 times 5.75 times 10 to the negative 10. X is therefore equal to 1.55 times 10 to the negative 5. All right, so remember X is our concentration of OH. So concentration of hydroxide ions is going to be equal to 1.55 times 10 to the negative 5. Now, what's the question? Let's just have a look here at what we're going to try and do here. What's the pH of this solution? Okay, let's work out pOH from our concentration of hydroxide. pOH is equal to the negative log of that we just worked out, which is equal to 4.8. That's our pOH. pH is 14 minus pOH, which is 4.8. pH is equal to 9.2. That's our answer. The correct answer is C. Now, you might have taken a 50-50 guess and guessed that one correct, but if you wanted to work it out fully, and it's good practice to do this anyway, that's how we get from point A down to point D to work out the pH. Given pKa, turning that into a Ka, turning that into a Kb, putting it into our equilibrium expression, solving for X, finding pOH, and from pOH finding pH. So quite a few steps for 1 mark, but it's chemistry. It's always fun to do, I guess. So this is a little bit of a different titration problem here. When you read through the question, it's not actually a neutralization. Well, there's a neutralization reaction, but you haven't neutralized and reached an equivalence between these solutions here, these concentrations of base and acid. It's just saying at this point of the titration, which one's in excess, and therefore calculate the pH. That's all we need to do. So we've got a balanced chemical equation here. We're not going to use the molar ratios because, again, we haven't reached an equivalence. But it is also, it's good to have that balanced chemical equation so we can visually see what's happening. Also good to see visually, particularly for this one here, there's volumes and concentrations all mixed into this question here, and it's hard to visualize what's going on. So again, pardon me, I'd recommend maybe sketching out your burette, conical flask, and let's start visualizing which concentration and volumes are where. Where's my acid? Where's my base? And let's have a look at the question. So at some point, we have 1 mole of sodium hydroxide and sulfuric acid. It's 3 ml of the sulfuric acid. Let's just find out where's the acid and where's the base. Sulfuric acid had been added from the burette. All right, let's just say in here in the burette we have H2SO4. Rightio, so that must mean sodium hydroxide in the conical flask. In here, we have our sodium hydroxide. All right, that's a good start. Now, we've got 1 molar sodium hydroxide, so this is 1 molar. And sulfuric acid, known by the teacher to be 2 molar, so H2SO4 is 2 molar. 3 ml of the sulfuric acid had been added, so sulfuric acid we have 3 ml. And what have we got down here? 10 mil of the sodium hydroxide in the conical flask. So this is 10 mil. Okay, so total volume 3 mil is 13 mil in the conical flask. Okay, now at this point of the titration between these two concentrations of base and acid, what would the pH be if we put a probe in there? Well, we need to start working out number of moles and see which one we have in excess, basically. Do we have hydroxide or do we have hydronium ions in excess? Let's start with the sodium hydroxide and work out the number of moles. Remember, titrations are all about moles, and we need to see which one of those moles we have left over. So the number of moles of sodium hydroxide, NaOH, is equal to 0.01, which is our 10 mil. So volume times concentration was 1. So we have 0.01 mole of NaOH. Rightio. Now let's work out, first of all, we're going to work out the number of moles of, we'll do it in a two-step fashion. Let's work out the number of moles of H2SO4 added. Let's just start here, and we say volume is 3 mil, 0.003, times the concentration, which was 2 molar, gives us 6 times 10 to the negative 3 mole. Okay, now we're actually interested in the number of moles of hydroniums or H's, and for each one H2SO4 we get 2 hydronium ions. So let's work out the N of H+. That's going to be 2 times the number of moles of H2SO4, because there's 2 H's in every H2SO4. So 2 times 6 times 10 to the negative 3 is equal to 0.012. 0.012 mole. So this middle step here was to work out the number of moles of H2SO4. This next step was to work out number of moles of H+. Because it's a diprotic acid, we had to do that second step. All right, now let's see which one we have in excess. We've got 0.012 of H+, and we have 0.01 mole of NaOH, or in other words, OH. So actually, you know what, I might put at the top here. So the concentration, therefore, of OH, because it's a 1-to-1 ratio of sodium to hydroxide, is also equal to 0.01. Number of moles, not concentration. So 0.001 mole of OH, not concentration. So let's work out which one we have in excess. We have 0.012 mole of H minus 0.01 mole of hydroxide, which gives us a 0.002 mole 0.002 mole of H in excess. All right, now we can work out the concentration of H3O, and if we work out the concentration of H3O, we can work out our pH, which is what the question is asking us. What would the pH of this mixture be at this point? So let's work out our concentration of H+. We have concentration of H+ or hydronium is equal to C equals N over V. We have N, which is 0.002. So that's going to be 0.002 over our volume. And remember over here, we worked out that we had a total of 13 mil. So that's 0.013 litres, which gives us 0.1538 mole. That's our concentration of hydronium ions, or H+. Next step, pH. pH, and this is our last step, is the negative log of that, which equals 0.81. Okay, so the answer to this question is A. 0.81 is the pH of this mixture in the conical flask. So remember, this wasn't a equivalence reached. We're not using a molar ratio. We're looking at how many moles of hydroxide and hydronium were put into that solution, how much cancelled each other out, which one did we have in excess. H2SO4 was diprotic, so we had to double the number of moles of H2SO4 to get our number of moles of hydronium. And then it was a simple matter of working out concentration of H plus and finding the negative log, which is 0.81. So again, this little problem here is let's just throw some acid and base together, see which one we have left over, and then calculate pH from that. So we need to calculate number of moles of hydroxide, need to calculate how many moles of hydronium, find out which one we have in excess, work out pH from that. So fairly straightforward. Excuse me. Let's work out our volumes and concentrations to start with so we can visualize what's happening. In a beaker, enough sodium hydroxide. So we've got 50 mils in total, and we had H2SO4, we had sulfuric acid in here, and how much did we have? 10.5 mil. We'll turn that into litres now. Why not? 0.0105 litres of it, and we had, what was the concentration? 0.0355. All right, now the rest of it, the rest of the 50 mil was made up by sodium hydroxide. So this is NaOH, and to make up the shortfall to 50, we would have added 0.0395. So 39.5 mil, 395 litres. Concentration of that was 0.0288 molar. Okay, so that's what we're looking at here. Now, again, we just got to work out moles of hydroxide, moles of hydronium, which one's left over, calculate pH. Moles of hydroxide is fairly straightforward. We'll do that one to start with. For each mole of sodium hydroxide, we're going to get one hydroxide. So let's say the number, the number of moles of hydroxide is equal to C times V. Concentration was 0.0288 times V, 0.0395. And that is equal to 1.14 times 10 to the negative 3 mole. Okay, so that's the number of moles of hydroxide. Let's see how much hydronium we had. Now, H2SO4 is diprotic, so if every mole of H2SO4, we're going to get 2 hydronium. So let's say that the number of moles of H3O here is going to be 2 times concentration times volume. 0.0355 times 0.0105, which is going to be equal to, let me just work this one out, 2 times 0.0355 times 0.0105, 7.46 times 10 to the negative 4 mole. Okay, we have that many moles of hydroxide, we have this many moles of hydronium. It looks like we're going to have hydroxide in excess, but let's work out by how much. 1.14 times 10 to the negative 3 minus 7.46 times 10 to the negative 4 gives us, right, so I'll just write down what we just did there. We did 1.14 times 10 to the negative 3 minus 7.46 times 10 to the negative 4, and that equaled 3.94 times 10 to the negative 4 moles of, and we had, that was moles of OH. So that's what we've got left over after neutralizations occurred. We've cancelled out a number of moles and worked out we've got this many moles excess of OH. Okay, so let's work out, if we've got a number of moles, we can work out the concentration of OH, then work out POH, then we can work out pH. So C, concentration of OH is going to be equal to N over V, which is going to be equal to 3.94 times 10 to the negative 4. That was the number of moles of OH. And we had 50 mils in total here, so that's 0.05 divided by 0.05 equals 7.88 times 10 to the negative 3 POH is equal to negative log of that, 2.1. The pH is equal to 14 minus that, 11.8. pH is equal to 14 minus 2.1 equals 11.8. The pH of the remaining mixture here, which is what the question was asking us, is 11.8.